So, today we are in our experimental condensed metal lab. So, here we will demonstrate how to determine the permeability of air. So, we have experimental setup. This is the experimental setup for measuring the permeability of air. So, I will explain this setup, but before that let us see what is the working formula for this experiment. So, this this permeability is the ability of the material to allow the magnetic lines of force to pass through it, okay. So, to determine this permeability, here method we will use, that is basically force between two long parallel straight current carrying conductors. Okay. So, any current carrying conductor, whether it is straight, circular or spiral, so it produces magnetic field. So, if you pass current through a conductor, it will produce magnetic field, right. So, that means the conductor behave like magnet when current is flowing through it, right. So, we are getting when current pass through a conductor, it produces magnetic field, means it behaves like a magnet. Now, if we take two conductors and placed in parallel, and if you pass current through it, so both of them will be like magnet. So, two magnet, if you bring them closer, so either they will repel each other or they will attract each other depending on the polarity, right. So, south pole or north pole, whether they are facing each other, or this south south north north, if so, then it will repel each other, okay. South north will attract each other, okay. So, force between two long parallel straight current carrying conductor, so that will be placed with some gap. Now, if you pass current through these two conductors, so either they will repel or attract depending on the direction of the current in the conductor, okay. So, this from Biot-Savart law, one can find out the magnetic field surrounding of a straight current carrying conductor. So, two straight circular or spiral current carrying conductor attract or repel each other as two magnet does, right. When two magnets are close to each other, then whatever the property phenomena we see, so two current carrying conductor will behave in same way. So, this is the fundamental basic concept of producing magnetic field in a current carrying conductor, okay. So, basically we use the Biot-Savart law to find out the magnetic field. So, here, so this a conductor, its length, say it's L, and current is flowing these two conductors. So, they are separated, this distance is D, okay. So, this center to center, this this axis of this wire and this of the other wire. So, distance between these two axes, middle point of each wire. So, that distance is d, and so d is basically d0 plus r1 plus r2. r1 and r2 are the radius of wire 1 and radius of wire 2, and d0 is the gap, gap between these two conductors. So, effective distance between these two conductors is d. So, that is d0 plus r1 plus r2, right. So, Lorentz force between these two wires when they are carrying current I1 and I2 in these two conductors. So, this force between two very long wires are basically, this is the formula, F equal to mu 4 pi 2 I1 I2 L divided by D. L is the length of the wire. This I1, I2, as I told, this current passing through these two wires, wire 1 and wire 2, and D is the distance between these two wires. Okay. So, distance is taken from the axis. So, here we have ear gap. So, basically we have ear medium. So, ear medium has permeability. Okay. Whenever magnetic field passing through a medium, so that property of this medium is expressed by permeability, as I told earlier. This permeability is the ability of the material to allow the magnetic lines of force to pass through it. Okay. So, here basically lines of force is produced by this, magnetic lines of force is produced by this wire 1 and wire 2. Okay. So, they are passing through this ear medium. So, that is why this concept will be used to measure the permeability of ear, right. So, in this formula, this mu is the permeability. So, here medium is ear, so permeability is mu of the ear, right. So, this, if current are same in these two wires, I1 equal to I2 equal to I. So, then we can write 2 I square L by D and 4 mu by 4 pi it is there. So, ultimately then we can write mu equal to 2 pi D by L F by I square. F is the Lorentz force. Okay. So, this is the basically working formula for this experiment, that mu equal to 2 pi D by L F by I square. So, D is the distance between these two wires, gap between these two wires, and L is the length of the wires. Okay. So, if this is the working formula, so from this working formula itself you can see what you have to measure. We have to measure D, and in D there are 3 parts. One is D0, R1, R2. So, obviously R1, R2 is the diameter radius of the wires, R1, wire 1 and wire 2. So, we will use screw gauge, basically we will use screw gauge. in our, so one can use slide calipers also, but here screw gauge is convenient and more accurate. So, we will use screw gauge for measuring the R1 and R2, and D0. How to measure this D0, that I will tell you. And second, you have to measure the length. You have to measure the length of this wire. Okay. So, that we will use this meter scale for measuring the length, and main part of this experiment is f by I square. So, we will vary I, okay, and measure the f, or we will vary f and measure the I. So, this f by I square basically will at least will take 4 to 5 to 6 set of data for each set of data. So, we will for a particular f, we will find out the current, how much current for that force. So, this will select 4 to 6 force, and we will find out the I. So, that is the main part of this experiment, and then we will plot graph f versus I square, graph, and from that graph we will find out the slope. So, if you find out the slope, that slope is basically f by I square. So, f by I square, that slope we will use here, and then length we know we will measure, and d also we know, for that d0 we have to measure, right. Now, let me show you first this experimental setup, and then I will tell you how to measure d0 and how to do this part, this f by I square. So, this slope, how to find out the slope, that I will explain. Okay. So, let me show you the setup for this experiment. So, here if you see, so these two wire 1 and wire 2, whatever I told during theory discussion. So, here this is this you can see a rectangular shape of a wire, and below of it there is another wire. So, here this wire 1 and wire 2 is basically, let us say this below one bottom wire. Okay. So, this is the wire number 1, and this top one, this is the wire number 2. Okay. So, two parallel wires, whatever we are telling, so that length are same for these two wires. So, basically the common length of this wire will be taken as a capital L. So, here common length is, you see, between this length between these two end, So, this part is the common length for these two wires. So, these the two wires whatever we are speaking. So, it has it's a rod kind of things, it's between rod and wire. So, its diameter or radius is between wire and rod. So, so these two wires, it has radius. So, this radius is not very small, but it is reasonable radius. So, we will use screw gauge, for measuring these wires. Okay. So, let us just first take this data. So, this is the digital screw gauge, I have not shown you earlier. So, let me show you. So, this is the digital screw gauge, it is on off is there, I think, yes. So, this digital screw gauge, okay. So, this reading is 0, this reading is 0. So, if you just rotate it, it's now here there is no gap. If you just rotate it, then you see this is changing reading depending on the gap, right. So, what is the reading now? Reading I can see this is 1.019 millimeter, 1.019 millimeter, okay. So, that means its least count is of the screw gauge is 0.001 millimeter, okay. So, 0.0001 centimeter. So, it's our this manual screw gauge, its least count is 0.001, but this digital one even it is more accurate, okay. Its least count is one order of magnitude is smaller, 0.0001 centimeter, okay. So, we will use this one. So, just you should measure the here, yes, I should measure, okay, this way. Oh, it's we have to, okay. So, yes, I think, yes. No, it's got stuck, it seems. Oh, it's okay. So, this is the crude one and this is on the finer one. So, I should rotate this one, not I was rotating the wrong one. So, I think yes. Okay. So, this more or less is giving reading 3.050. So, this way in 3 places we will take this reading for wire 2 and 3 places we will take reading for wire 1, this bottom wire. So, here I have to just I have to put here, okay. Yes. So, this way we will find out R1 and R2, whatever in formula I have showed you R1 and R2. Here D equal to D0 plus R1 and R2. So, this way we will find out R1 and R2. Okay. So, now so these two wires, it has gap between this air gap, that is D0. That D0 how we will measure, that I will tell you. Now, we have to pass current through it. We have to pass current through these two parallel wires, straight wires. Okay. So, we have here is you can see this high current power supply. So, so this here I can see this, it can give maximum 20 ampere current, 20 ampere current. So, this you see this one connection and this is the another connection, this is the another connection here, another connection here. So, this and then since we will pass the same current in the both wires, I1, I2 are same. So, if I connect current here from this source, so this from this source I think I have to check some arrangement is done. Okay. So, basically here this yellow one is coming here and the red one is coming here. So, current is say entering here and then passing through, I think this is connected here. Okay. So, passing through this, passing through this, passing through this, and then here I can show you there is connection here and here. So, current will come out through this, current will come out through this, and this is the current will come this way and enter here, and this will go this way and go out through this yellow wire. Okay. So, this is the complete circuit. So, same current is basically passing through this to the top wire and to the bottom wire. Okay. So, current will pass here. So, connection we have made in such a way, if current entering here, so current direction is this, and then I told you this way it will follow the black wire is coming here and then current is flowing this way, then it will come out through the yellow wire. So, here you can see this in top wire current is passing through in this direction, and bottom wire current is passing in opposite direction. So, when current are flowing through the opposite in opposite direction, then there will be repulsion between these two wires, and if they are passing through the same direction, so then they will attract each other. Okay. So, but there is a reason why we are taking in opposite direction. Reason is that if they attract each other, then what will happen? They will touch each other, there will be short circuit. Okay. So, to avoid it, just we have chosen the opposite direction. Taking in same direction also one can do the experiment, but as I told this, you have to be cautious. There should be you should take precaution, okay, to avoid such accident, that if they touch each other and high current is flowing. Okay. So, then there will be, maybe when they will go very close, then there will be sparking also. Okay. So, to avoid this, it is better to choose current in opposite direction, then you will get here you will get this repulsion between these two wires, and they will go I think in opposite direction. Okay. So, there is no possibility to touch each other. Okay. So, now here, so this fine, these two parallel wires, and we have arrangement for current passing through them in opposite direction. Now, this wire, top wire, bottom wire is fixed, okay, constant fixed, but top wire, this arrangement is done in such a way that this basically it can rotate freely. This top wire can rotate freely. So, it is here we have basically here this lever kind of arrangement is there. So, this wire you see is connected with these other two wires, and here we have made the arrangement, lever arrangement, so that this can rotate or oscillate freely with respect to this axis. With respect to this axis, it can rotate freely. Okay. So then we have option to balance it. It's a to fix the ear gap. So there are options here. One can increase the gap, one can decrease the gap. Okay, but here we have fixed that gap. This is the gap between these two wires. So now we have to measure the gap between these two wires. Okay, so for that, basically we have taken light mirror arrangement. So the one mirror is fixed with this lever. Okay, here it is fixed. So if it is rotate, if it just oscillate, you see it's oscillating. You can see it's oscillating, right? It's oscillating, right? And this mirror also oscillating because it is fixed with this frame. So it is also oscillating. So it's a oscillating, it's a rotating with respect to this axis, and on the axis itself, near the axis itself, we have mirror fixed with this. So that also oscillating with this same way. Okay.